This presentation focuses on our RSS 2020 publication on compositional transfer in hierarchical reinforcement learning. It is work with everyone you can see on this slide and many others at DeepMind contributed on the infrastructure side to enable these experiments. The direction is relevant to us because compositionality can help to save significant training time for real robot setups purely based on simple extensions of our training paradigms and finding a robust algorithm to train hierarchical compositional policies. We focus on hierarchical mixture policies as they can provide a middle ground between monolithic and independent policies for multitask reinforcement learning. The multiplicative relation between component probabilities and probabilities of actions under these components for mixture distributions enables easier representation for strong changes in the relation between observation and action. With specialized components, we later show that the high-level controller can more quickly compose solutions to new tasks. To train mixture policies, we introduce an actor-critic method which relies on a critic-weighted maximum likelihood estimation update procedure. We can use trajectories to train all components, independent of which mixture component generated the data. Furthermore, this formulation requires no relaxation for the categorical distribution. Additionally, in the multitask case we assign rewards for all possible tasks to trajectories independently which task's policy was used to obtain the data. In RHPO, we first compute a non-parametric, improved policy based on samples from the previous parametric policy weighted by the critic. Second, we minimize the KL divergence between the non-parametric update and the parametric policy. In other words, we maximize the likelihood of samples from the non-parametric policy under the parametric one. To encourage the specialization of mixture components, we utilize information asymmetry and only provide task information to the high-level controller. For our experiments, we first consider the single task setting using two humanoid tasks from the DeepMind control suite. On the top right of all videos, you will see the currently active mixture component. In order to benefit from hierarchical policies in this setting, we need to introduce initial bias to the mean value of each component to encourage specialization, as shown by the red line in both figures. An implementation detail not necessary for the multitask domains. We consider several multitask environments for evaluation and start with a simple stacking domain with 7 tasks. Again, we observe considerable speed up when using RHPO instead of training flat Gaussian policies, here as monolithic policy shared across tasks marked as SAC monolithic, as well as independent policy heads marked as SAC independent. We additionally compare against the implementation from the original scheduled auxiliary control paper, which is based on SVG as policy optimizer for independent policy heads. We also adapt our algorithm by using SVG as policy optimizer for mixture policies, marked as RHPO SVG. In this case, we are required to use a continuous relaxation of the categorical distribution to train mixtures. One of the other more complex domains we consider is represented here by the cleanup domain with 13 tasks including interaction with a box and tasks for packing the objects. In this scenario, we see more significant gains by using RHPO. In general, more complex tasks or slower data generation benefit more from hierarchy. Most importantly, the approach accelerates training on the physical robot setup, here again with a stacking problem. In this domain, we can only use a single actor for our experiments and data efficiency becomes even more relevant. To provide a better overview of the challenge, you can see the range of all tasks in the Pile 1 domain here. Moving on to our ablations, one important aspect we investigate is the use of trust region constraints to control the change of the high-level policy. Very strong constraints can slow down training, but we find a range covering 2 orders of magnitude with strong performance. As an additional application, we also show that RHPO is suitable for sequential transfer by using pre-trained mixture components. Reloading components and only training the high-level controller can significantly speed up training. In some domains, where the final task is not well covered with the previous task set, we can introduce a randomly initialized and trainable mixture component to learn any additionally required behavior. We can compare components based on which tasks use them and vice versa. For example, we see that the second 2 and final 4 tasks are most similar to each other with respect to the skills they use. Finally, we can take the role of the high-level controller and use the skill space as a new interface for a human operator to control a complex system. Thank you for listening, and please visit our website for more information and videos.